Good afternoon and good morning, everybody. Thank you for joining our webinar today. My name is John Conboy. I'm the Sales Director for Middle East and North Africa for Danfoss Drives. Welcome again. Just to let you know, we're just going to wait 1 or 2 more minutes. There's a lot of people joining as we speak, and we'll just let the numbers build and then we'll start. Thank you for your patience. Okay, I think we can make a start. Thank you all again for joining. For those of you that missed it, my name is John Conboy. I'm the Sales Director for Danfoss Drives, Middle East and North Africa. And we welcome you to the very first ever Danfoss Drives Club MENA region webinar. So it's a very special day for us all that we've been planning for quite a time. So we thank you for your attendance, and we hope that the club and indeed the seminar will be of use to you. So if we can flick forward to the next slide, I'll just maybe share some of the practicalities for today. So you've all been muted by us just to make sure that we don't have any background noise, but you are able to unmute yourself, or to, if you have any question, maybe raise your hand first of all, and then also you can type a question into the questions tab on the tool. So Gregors will be the main presenter today, and throughout his presentation we will take time to look at what questions are there, if anybody has raised their hand, and so on. So the webinar is recorded, and we will be sending you the presentation file shortly after today's webinar. So next slide. Here I just want to give a brief introduction to some of the Danfoss MENA team in Drives. I've introduced myself already, John Conboy, Sales Director for Middle East and North Africa, and to my right you can see my colleague Moaz Al Ibrahim. Moaz is business development for MENA region, and somebody that you will interact with frequently throughout our journey as part of this Drives Club. We also have on the phone today, we have Farouk Muhammad Ali, who's the country manager for GCC countries excluding Saudi Arabia. We also have Ibrahim Kamal, who's our country manager based in Riyadh for Saudi Arabia and Egypt. And finally, we also have Vedat, who is our technical manager and will be handling any of the real deep technical topics that we might have during our discussions as part of Danfoss Drives Club. Next slide. Just want to give a very brief introduction for those of you that don't know to Danfoss Drives. Last year we had 1.5 billion euro in revenue. This makes us globally the #2 drive supplier in the world. There's a very little margin between us and the #1, only 1%. And so we have a strong ambition, of course, to be the #1 drive supplier in the world. And we believe that we're well placed to do that. We've delivered close to 25 million drives since we started. And we had a little bit of head start, of course, because we were the first company in the world to mass produce VFDs. As you can see, bottom right hand corner, we started mass producing VFDs in 1968. And we have a long history in drives and drive technology, and a vast amount of experience. And of course, in 2014, Danfoss acquired Vacon drives. So those two brands and those two portfolios are what we run today. And between those two companies, we have a huge amount of drives expertise and experience. We have over 1,000 partner companies globally, and we're present in over 100 countries. So we're covering every corner of the world, every industrial application, every light industry, heavy industry application. Anywhere really you have an electric motor, you can of course have a variable frequency drive. So that's really it on the Danfoss side. It's a very, very brief introduction. Now I want to talk a little bit more on the next slide about Drives Club. And first of all, we'll watch this short video, and then we can have a little chat about as to what exactly Drives Club is all about.
Variable frequency drives have the potential to reduce the world's electrical energy consumption by 8% by 2040. Today, drives are so much more than an energy efficient device. They've become an intelligent device that can optimize your entire process and a smart sensor that can monitor the health of your full application. Danfoss were the first company in the world to mass produce variable frequency drives over 50 years ago. So we've accumulated a huge amount of experience in that time, and we would like to share that knowledge with you. If you specify or work directly with VFDs, then join our Danfoss Drives Club. You will get exclusive invitation to regular webinars and access to a host of technical resources. All our webinars will be presented by global experts and will be CPD approved. If you're based in the Middle East and North Africa, then sign up today.
Great. So yes, so drives have been around a long time, and I would say if in a brief history of drives, we can see that the first years were really to progress on the hardware and get the reliability correct. And then once that happened, then it very much moved into more of a software feature. So we started to develop dedicated software features for specific applications in specific industries. And now we're moving into much more of the connected device and process optimization. So the advances in drives that we're seeing in the last couple of years have really accelerated and will into the future. And that's why we came up with the idea of Drives Club, is to really to keep the industry abreast of what's happening out there. And so Drives Club is all about bringing drives enthusiasts together. We're a forum to discuss technical topics. Our members are typically electrical or mechanical professionals from several types of company types: consultants, contractors, system integrators, academics. And the club is well, we're meeting virtually today. Of course, this would have been intended to be a physical meeting, and possibly a hybrid of physical in Dubai and virtual for the rest of the MENA region. But we do intend to move around the MENA region when we have that possibility. And that will be a quarterly event. And then, of course, we will have regular newsletters and white papers on specific technical topics. And the idea of the forum and the club, everybody, is really that we engage with each other and we have a dialogue. So we really hope today that there's a lot of open questions, and feel free to raise your hand and get involved in the discussion. We have a fantastic speaker in Gregors. Gregors is an expert on harmonics, and one of the most interesting people I've heard speak on the topic, because it does get quite heavy and quite technical. I've listened to a lot of people discuss the topic, but I feel that Gregors has a fantastic slant on how to do that. So as I say, Drives Club is all about us coming together as a group in a forum to discuss, and so we hope that we get an open dialogue today. On the next slide, I've already a little bit introduced Gregors. Gregors is based in Denmark and been working in Danfoss for over 20 years. And as I say, has been deeply involved in harmonics and developing our harmonic portfolio over those years. And today he's the head of the water and wastewater portfolio, but he's had many different roles inside Danfoss in the company over that period of time. So without further ado, I will hand over the microphone to Gregors, and yeah, over to you, Gregors.
Thank you, John. So thank you all for joining in today, and I've been looking forward for this meeting and having the ability to talk a bit about harmonics and trying to show you what we are doing and especially some of the capabilities that we have. As already mentioned, harmonics can be quite difficult topic to understand. I'll try to make it as easy to understand as possible, leaving a lot of the math out, and simply go down to the key of the topic. There has been some specific requests on approvals and IEEE norms, so I'll try to go into detail there a bit. It's maybe not the most interesting topic to talk about, but it's definitely important. And IEEE standards is what we normally meet in the market, and this is of course essential to understand. So before we go on with the presentation, we will start this with a little poll. Just to make sure that you are also active while we are having the presentation.
So Gregors, are you able to see the poll results?
No.
Okay, yeah, that's a little bit difficult with the GoToWebinar, but I can just jump in and say that 33% have specific examples where harmonic distortion has caused issues, and then we have 57% have said that I've seen issues that they think that they're related to harmonics, and then there's about 10% of the audience that are not sure. So yeah, it seems that the majority of the audience have had harmonics issues in the past.
Okay, thanks. So now maybe I'll destroy your picture a bit when we go a bit further and actually show you, maybe you have more issues than what you expected. But before we get started and talking a bit more about harmonics, I will actually start talking a bit about how the drive is built up. So when you have a VSD or a switch mode power supply or a fluorescent light installation or a UPS installation, you will see a circuitry similar to the one that you see on the left hand side. And what we have over here is 6 diodes, and that's the ones marked with 1 to 6. And that is actually the main components of the input stage of a frequency converter or VSD. Additional to that, we have a capacitor in the DC link, and of course you can size this capacitor indifferently. So depending on your drive brand, you will see different capacitor sizes. You can also have other components in the DC link. For instance, at Danfoss, we as standard have built-in DC chokes as well, so there will be an additional choke here, which we have built in to reduce the harmonics. But for the example here to begin with, I actually took the most simple application form, or the most simple build-up, with 6 diode and a capacitor. The way that the current goes into the frequency converter, the way that the diodes are ducting, means that we are not pulling sinusoidal current from the grid. For the current to go into the DC link, the current or the voltage on the input side needs to be higher than the voltage on the DC side. And that means that we only have a very narrow window of time where this behavior is in place. And that basically means that the current that is pulled from the supply line is a pulse form that you can see below the picture here, the green curve here with 2 positive pulses followed by 2 negative pulses. So if you take a VSD and you map the current in front of the VSD, you will see a pulse shade similar to the green curve that you have underneath here. You will see the same if you took a switch mode power supply. Of course, if it's a single phase, it looks a bit different, but for 3 phase devices, it looks the way that you have down here. Now, every component that has this kind of behavior is referred to as nonlinear. And there is, as said, a lot of these non-linear loads on your supply or on your network, and they all draw non-sinusoidal current waveforms. And that's actually what we need to look at now. What happens? What is the flip side of these non-sinusoidal current waveforms? First of all, if we look at the normal way of describing harmonics, it's done by abbreviation or a short called the THDI value, the total harmonic distortion of the current. You can also talk about the total harmonic distortion on the voltage, and then it's just THDV. But it's basically the same thing. This impression here or expression here tells you how far away the signal is from the ideal sinusoidal waveform. So if we take, for instance, the example you had before, the green curve from a frequency converter, and you want to see how distorted that is, then you need to do some math on it. Normally we do that by helps of Fourier analysis or fast Fourier transformations. And what we basically do is we're trying to represent the distorted current waveform by a sum of sinusoidal waveforms. There was this French mathematics that found out that you can represent any given signal in terms of sinusoidal waveforms as long as they are repetitive and continuous. And if you had a signal like we had before, you can actually represent that not by one current waveform, but by a sum of sinusoidal waveforms. So that is actually what I'll try to do now. I'll try to generate the current waveform you saw before by adding sinusoidal waveforms together. And the first waveform that you see here is a nice looking sinusoidal waveform. It has a frequency of 50 Hertz. It has an RMS current around 40 amps, and it's ideal. So it's perfectly sinusoidal shaped. And that means that the THDI value or the THID value is 0. So it's perfectly sinusoidal shaped. If you look at the frequency spectrum down here in the lower hand side on the right, you can see that the 50 Hertz is represented by 100%. So every additional curve that we add on top of this is sized according to the fundamental frequency, or the first harmonic as we call it, which has an RMS value of 39 amps. So the next signal that we add on top is now what we call the seventh harmonic. And in this case, it's the fifth harmonic, sorry. So the fifth harmonic in this case has 5 times the fundamental frequency. So if the fundamental frequency was 50 Hertz, this frequency is 250 Hertz. So the sinusoidal waveform that I added on top of the other one has a higher frequency or a faster frequency than the fundamental frequency was. And when you add those two frequencies together, then you will have a sum waveform looking like the one you have down here. What you also see now is that the RMS current went up. So we went from 39 to 49 amps, and the THDI value went up to 80%. That means now that if you look at this waveform here in the middle, you can say that it's 80% distorted from the ideal sinusoidal shape. Now I'll add a few more harmonics or a few more signals on top of it. Now I added the seventh harmonic or the seventh order frequency. So 7 times 50 Hertz is 350 Hertz. When you add these three together, you have a curve looking like the one you have in the middle. You can see the RMS went up again and the THDI went up again. I add another frequency now, and you are almost seeing a representation of the green curve that you had to begin with from the frequency converter. Simply by adding 4 signals together, we have actually represented the almost the current waveform that we wanted to represent. The order that we just added was called the 11th, so 11 times 50, 550 hertz is the signal frequency of that one, and you can see the amplitude went down. So you will typically see when you're talking about harmonics that the first is the highest, and then the following order is declining, and it's getting smaller and smaller and smaller, the harmonics. So that's typically what you see when you have a system like this, that the peaks, the individual peak harmonics are reduced the higher the order get. So now I'll stop here. You can see here the RMS current went up. So the current that the frequency converter is consuming, the green curve you saw to begin with, is actually pulling 55 amps from the power supply. We are only using the 39 amps for generating torque to the motor, whereas the 55 is actually what we are blocking from the power supply. And that basically means that the power supply or the power utility has to deliver more current than what we are consuming in the frequency converter for generating torque to the motor. So you can say we are blocking an overproportional amount of current from the power supply by simply because of the way we are pulling the current from the supply grid. In this case, it's 43% higher, so it's the 55 amps, it's the square root sum you calculate it by, so that's how you get to the 43% higher RMS current. So basically, when we're talking about harmonic currents, the problem here is that you need to size everything in front of the frequency converter for a higher current. That means that the cables need to be able to take the extra current, the switchgear needs to be sized for the higher current, and the transformer needs to be sized for the higher current. And that basically means that you need to oversize your component when you have a lot of current distortion on your supply network. To overcome this, as said earlier, we at Danfoss has always built in a DC choke, and that means that you will not see this phenomena. You will see an RMS current that is only slightly higher than the fundamental is, meaning that you don't need to oversize when you're buying a frequency converter from Danfoss. And the reason for that is that we have the built-in choke inside the drive. So in order to avoid having to over-specify or over-engineer the input side using bigger cables, bigger transformers, bigger switch gears, I urge you always to buy a drive with a built-in DC choke, simply to avoid this phenomenon. The problem with harmonics is, however, not on the current. The problem with harmonics is actually due to the voltage. So if you look at your normal system supply, you will see that you have maybe one drive supplying a motor, and then you have a lot of direct online motors supplied from the same transformer. If you take this example you have on the right, we have one drive only. We have a voltage distortion of 5%, and you can see the direct online motor that is pulling the supply power from the transformer is fairly cool. So if you look at the picture here of the motor, you can see that the motor is not heated up. It's not very red, indicating that the motor is quite cold. The motor is having good running conditions. If you take another scenario where you have now added more drives to your installation, you can see that the voltage distortion increases. So now the voltage distortion went up to 8% because you added more drives that distorts the current more. And when you have more current distortion and you have Ohm's law saying that the voltage distortion is depending on the current distortion by the system impedance, then that means simply that now the direct online motor is seeing a worse voltage signal. And that means that the motor now is actually becoming a lot more hot than it was supposed to be. It's running at the same loading condition, nothing has happened to the motor except that the voltage that the motor is supplied with has a different part or a different harmonic footprint. So the voltage distortion is higher in this example here, but nothing has changed on the loading of the motor. So the flip side of harmonic is actually not something that starts falling out of synchronism. It's not something that caused sudden production stop. Harmonics, the typical side effect of harmonic is reduced energy efficiency of your installation. In this specific case on the motor, it probably means that the bearing in the motor here will wear out because the bearing is becoming a lot more hot than it was before. So the effect of harmonic voltage distortion is not necessarily something you will see instantaneously, but something you will see over the lifetime. So you'll see reduced lifetime of your equipment. You will see risk of bearing stress. You will see risk of winding insulation issues in the motor and so forth. And that's the reason why it's essential that you try to reduce the voltage distortion in your installation. As said, the current distortion we have already, as a supplier, taken care of. We have built in the DC choke, but we will not be able to reduce the voltage distortion of your installation because it depends on your installation conditions. And that's represented by this impedance value that you have in Ohm's law here in the graph. And that unfortunately also means that you will, for your installation, have to go in and analyze if you will get into issues with voltage distortion or not, simply by specifying what your conditions are for the given installation. You can, of course, always try to reduce the current distortion to a minimum, and that will help you on the voltage distortion, but it's just a very costly way of reducing harmonics, and in many cases, it will actually not help you. It'll just make your installation more expensive, and it'll add more equipment to your installation. That means that the installation is getting less reliable, and there is a tendency of products failing faster when you have more equipment in your installation. So the best way to reduce harmonics and ensuring that you're not getting into harmonic issues is actually by doing analysis of your installation. You need to go in and say, is it safe for me to run under these circumstances that I have? There is actually a IEEE standard saying how much you're allowed to load your motor when you have a given amount of voltage distortion. You can find some curves in the standard, and the curve actually tells you that if you have 88% voltage distortion, you shouldn't load your direct online motor with more than 85%. And of course, if you have 10, that number has dropped down to 75%. As we are often met in the market with requirements of meeting specific standards, I would like here to explain a bit about the standards that you normally meet in Middle East and Africa, which is the IEEE 519 recommendation. The IEEE 519 recommendation is not a product recommendation, it's a system recommendation. And that means that it doesn't apply for individual products. It applies only for your installation. And that means if you have 1,000 drives and 1,000 direct online motors in your installation, then the IEEE 519 standard applies for the 2,000 pieces of loading you have on your installation, and not for the individual 1,000 drives in isolation. And that's extremely important to understand, because if you start now mitigating each and every harmonics on your individual loading, then you will end up spending a lot of money on something that doesn't give you any value. IEEE has one overall arcing goal, and that is to reduce the voltage distortion. So the overall goal of IEEE, you can see here on the left-hand side, that is actually that you should avoid that the voltage distortion on your power supply is more than 8% or 5% for the individual order. This is actually part of the updates that this 5 and 8% was added to the standard. Before that it was 3 and 5%, so now we allowed a little more distortion on the power grid compared to what we had before. As you can also see here, it depends a bit on where you connect. So if you are connecting on medium voltage, then you are allowed less distortion level. And if you're connecting to high voltage, so now we're talking about 100 kilowatts, then you are allowed even less distortion. And the reason for that is simply that you would like to have less and less distortion the higher in the voltage you get, simply because you are distributing the voltage to more consumers. And simply that's the reason why you are going down in distortion, maximum distortion levels. But for your typical applications where you're connecting to 400 volts or 460 volts, you have to ensure that your distortion level on the voltage is not exceeding 5%. How much current distortion you are allowed on the transformer depends a bit on your short circuit ratio. So you need to understand what your short circuit ratio is for your installation to be able to evaluate what the maximum current distortion is. And if you look at the lower level here, you have a table showing you the maximum allowed current distortion level depending on your system short circuit impedance, or your system short circuit ratio, sorry. If you have a very big transformer, then you will normally see that the short circuit ratio goes up a bit, and that means that you are allowed more distortion on a bigger transformer compared to a distortion level on a small transformer. But again, it depends on how much you're loading the transformer. What's also important to notice here in the standard is that this is for 95% weekly loading. So you are allowed short-term peaks. So if you have something that loads the transformer more for a very short period of time, that could be a run-in situation, that could be a short-term overload of your transformer where you need to loosen up a tension or something, then that is allowed in your installation and still complying with IEEE 519. So we're not talking about overload situations, we're talking about normal running conditions. There are also some specifics how much extra you are allowed. You are actually allowed up to 2% the values if we are to 99% of the daily loading profile. So that's some of the updates the recommendation has given for the newest update that we saw in 2014 on IEEE 519. But important to notice is that this is a system level demand and not on individual component level. So IEEE 519, 5% current distortion doesn't apply for one single loading on your transformer. It's for the combined loading of your transformer. Now, just to give you some guidelines to avoid that you have to go and do harmonic analysis on all and every installation that you're doing. I normally have a rule of thumb for when you need to do your calculations. First of all, you need, of course, to do your analysis, if you have to do the analysis at full loading. So the highest loading, where you see the highest impact on the voltage. You should try to reduce the voltage distortion to less than 5%. That's good engineering practice, and that's where you get the best cost performance balance. And you should not start compensating if it's not needed, simply because it's a lot of money you're wasting in that way. And maybe to give you a guideline also to when to do it. Whenever you're using Danfoss drives, you don't need to do harmonic analysis when your sum of drive loading is less than 40% of your transformer size. So if you have a 1000 kVA transformer and you have 400 kilowatts of drive loading, then you don't need to do your analysis, because then you're always safe. Then you're always having a voltage distortion level that is less than 5%. When you're now applying 800 kilowatts of drive loading on a 1000 kVA transformer, that's where you start having a need to do the analysis to see if you're good or not. So the 40% loading is normally what I advise customers and consultants to use, simply as a guiding star for when to do the analysis. When you do need to do the analysis, then you need to go in and do tools and use tools to do the calculation. And at Danfoss, we have various different tools available for you. It's freeware, so you can download them from the web. And it doesn't cost you anything. It's not that you have to pay a license fee or anything else. It's freeware that you can use. And it's built in a way that it allows you fast and easy overview of your installation. And I'll actually try to make a specific example. Now I'll have to maybe do it a bit slow to make sure that the internet is working according to specification. But what I've done here, I went into the Danfoss.com site, into the software part, and I downloaded the MyDrive suite. And after loading that, I can see all the different harmonic tools and drive tools that I have available in terms of software. And out here, I have the MyDrive harmonic tool that I click on, and then you're allowed to, or you're asked to install it. I have already installed it on my computer, so I can just open a file, and now I can create a project. So I'll create a project. It'll ask me some questions about my system, which frequency I'm using, the naming of it, if I want to use calculation on medium voltage or on low voltage. It'll ask me if I'm fed from a transformer or from a generator. It'll ask me where I want to do my analysis, because depending on different standards, there are different ways where your analysis needs to be done. And I normally take the transformer secondary side when I do calculations. It'll ask you which overall standard you want to comply with. And now I'll just take the IEEE or the EN61 standard as an example. And now I'm actually asked about the system setup. So these were some starting questions that you are asked simply to allow the calculation tool to set the right preferences for you. So now you have the ability to go in and analyze your system. So what you see here to begin with is an overview of your installation. You have a grid supply coming from somewhere. That's probably a power plant somewhere that is supplying your grid. And here it asks you what the short circuit impedance is on your power grid. Normally you don't have that value, so I recommend you just to use the standard that you have here. But the more precise you want the calculation, the more data you will have to enter. What I'm interested in is of course knowing what goes on in my lower level, so I'll go down to the lower level and I'll start by giving the information about the transformer. So here you will be asked about the transformer data, and that data you can find on the nameplate on the transformer, or you can ask your power utility. They have to provide that to you. It asks you which voltage it is you are having, so 400 volts. It asks you about the nominal power rating of your transformer, and I'll just take its 1600 MVA transformer, and it asks you about your short circuit voltage percentage of the transformer. So I'll use 5% in this specific example here. These three values that you are asked to enter here are nameplate data, so it should be quite easy to get from the power utility, or if you have the transformer in your facility, you can actually look it up directly. Then I have to add a few drives as well, and I'll do that here. in this specific example, I will just add a few drives, and I'll use the 202. So this is a water project, and let's just install, I don't know, 200 kilowatts and 4 of them. So now I have 4 drives of 200 kilowatts each installed on a 1600 kVA transformer. And now I want to see if that is generating problem to me or not. So I go back to the overall transformer and the grid overview, and I press the result button. And now the tool is calculating the effect of these 4 200 kilowatt drives on a 1600 kVA transformer. What the calculation overview tells me is I have a voltage distortion of 5.5%. I do comply with the EN 61000 standard. I have a current distortion on the transformer equal to 35%. I can also look at the individual harmonics. I can see how big the fifth is, how big the total harmonic current distortion is. I can see the current waveforms, the voltage waveforms, and so forth. All individual or all data that can be relevant to show and to know a bit about for your installation. So the result here, what that actually tells me is I have a 5% voltage distortion on my power supply. So it's higher than 5%, but it's very close to 5%. And I have a current distortion of 35%. So I would say for this specific example, I would not do any mitigation, because you are so close to 5% that it's probably not going to give you any issues at all. You have a very good power quality on this specific example. You can also see here the current distortion is 35%. So if you were going in and trying to achieve 5% current distortion in your installation, you would have to put in a lot of mitigation equipment. It would probably reduce the voltage distortion quite a bit, but it will not give you a more reliant and safe installation. So you will simply have to add a lot of equipment that costs you a ton of money without really giving you any benefits. So that's the reason why this is the important value to look at, the voltage distortion. Don't look too much on the current. It's the voltage distortion that is the important part of the installation. As said, this tool is free for you to try out and run. So you can go into your system, you can add different things to it. For instance, if I wanted to change the drive now to be low harmonic, I could do that as well. So I would go in here, I would disable those, and then I would install low harmonic drives instead. So now I'll use low harmonic drives instead of standard drives to get the 5% voltage distortion, or current distortion, sorry. So 4 of those instead. And then I'll go to the results, recalculate. So now I'm doing the calculation of what would it be like if I chose to use low harmonic drives instead of standard drives. What would be the outcome of it? And it just calculates for bits. So we need a little of patience here. It normally doesn't take that long. So actually in this example, it's quite an interesting example that we have here. Now you can see the voltage distortion actually went down to 2.5%. You can see that the current distortion went down significantly, down to 2.13%. But you can also see that we're actually not compliant with the standard anymore. So you have added mitigation equipment, but it has actually not made the situation better. On the contrary, it has made it worse. And the reason for that is because you can see that the low harmonic drive actually does impact the higher order harmonics. So everything is clean down here in the lower end, but you start generating more noise in the higher end of the spectrum. So that's also the reason why I'm trying to persuade to you that you need to be extremely cautious in what you're selecting. You need to make sure you know what you're doing, and you should only add mitigation equipment when it's really needed. And in this specific example, it's a pretty dumb idea to add mitigation equipment because you end up destroying your picture. If you have a resonance point on your supply grid now around the 41st harmonic, and that would be times 50, so what is that, 2 kilohertz frequency, then that will be erected by the harmonic here, and you will have an installation that might start giving you issues.
Gregors,
Yes.
before we jump into the poll, I have a lot of questions here, so maybe I want to queue
Very
some
good.
of them up. Yep. One or two of them I think we're going to handle a little bit later, but I have a few questions here on IEEE 519. Let's tackle those ones first.
Yes.
Here we go. Is IEEE 519 or any other standard calling for 5% THDI at the drive point or drive terminals,
No.
let's say?
No. There are product standards, and Danfoss comply with all the individual product standards. These product standards typically say that the current distortion of a device has to be somewhere lower than 40–45%. But there is no product standard saying 5% current distortion. None.
Yeah. Good. Then I have a question here. Does a passive filter solution meet or comply with IEEE 519?
In many cases, yes. We have various different types of passive filters. You can use both 12 pulse, 18 pulse, AHF filters, other parts or other kinds of passive filters. And depending on the dimension of the filter and the size of the filter, you will have them comply with IEEE 519 on component level. So yes is the easy question, or the easy answer to the question.
Good. And then I have some questions around chokes, AC and DC. I'm not sure if that's better later in the presentation or you want to take it now.
No, let's just take it now.
Okay. So it's kind of a two-part question. So the first part of the question is, for smaller powered drives, is it okay to have a drive without the choke, or any thumb rule on drive size to have built-in chokes? And then the second one is around AC and DC, and is there a difference?
Yeah. So let's start with the first one. Picking a drive without a choke. Again here, if you look at product standards that we have to comply with, there are actually special requirements if the drive is smaller than 7.5 kilowatts. So if you're below 7.5 kilowatts, you are actually allowed to build a drive without a DC choke. And you will also see that the micro drives that we are supplying, the FC51s, actually do not have an inbuilt choke if they are less than 7.5 kilowatts. But everything else has. I would normally not recommend to use drives without a DC choke, simply because if you add more of them together in an installation, you have a tendency of increasing your problem. So as a generic thing, I would say don't use drives without chokes unless you have very few drives in your installation. And then to the next question, DC chokes versus AC chokes. if you look at the harmonic footprint or the harmonic spectrum of these two versions, they are alike. So there is very little difference in the harmonic footprint of the two solutions. What you will see with a DC choke is that you have a slightly higher voltage in your DC link, and that means that you will actually normally see less current demand on your motor side. So you can have a little higher energy efficiency with a DC choke compared with an AC choke. However, the AC choke has some benefits when you have very fluctuating input grids. So if you have very much distortion on your input side, then a DC choke can sometimes be a better solution than or an AC choke can sometimes be a bit better solution than a DC choke. So there isn't a wrong and right. It really depends on the installation.
Okay, great. Just a couple of more before we move on. Is the short circuit percentage the same as the transformer impedance?
No, that's two different things. The transformer impedance is a value that defines how good the transformer is, how big the transformer is. Normally, if you want a lower impedance value, then you buy a better transformer, you can say. And again, here maybe something I didn't touch is actually when you have a generator, you will see that the impedance is much higher. So if you would run a situation that I had before, where I was actually okay without filters, if I tried to do the same calculation with a generator instead, then you would see that the impedance is much higher, and that would probably mean that I would not be okay if I was fed by a generator. The short circuit impedance of your installation is a value that it depends on how much loading you have on your installation. So how many motors do you have? How many drives do you have in relation to how big the transformer is? So that's more a ratio between the loadings that you have to know.
Yep. We've opened the floods again here, Gregors, which is great. We love questions, and so they're really flying in. So let's keep going with those. If we have harmonics produced by a load, but the transformer is isolated or isolating, do we still have to analyze the harmonics?
Good question. Normally, if you look at standards, you are actually allowed more distortion if you have your own transformer. You can say that everything that the transformer is supplying will see the distortion that you have generated. So if you envision the room you're sitting in, if you put a frequency converter on your table and you connect it to the nearest power outlet or the plug in the wall, then everything that is fed from the transformer will see the distortion that you have generated in your room. And it doesn't really matter if you have your own isolated transformer, whatever you have, it's everything fed from the same transformer. So even though you're sitting in your local room, it's actually also the room next door, even maybe the house next door or the factory next to you that will see the distortion that you have generated. And you need really to go up to medium voltage and down again to another transformer before you have smoothened out some of the harmonic distortions. So everything fed from the same transformer need to be analyzed at.
Yep, very good. Is there an international standard for harmonics in high voltage lines greater than 150 kV? Sometimes DSO, TSO criticize this behavior of the power electronics, VFD, wind, PV inverter, etc.
There are a lot of international standards on various different voltage levels. And EN has set regulations all the way up to 69,000 volts. So depending on how high you are in your supply voltage, you will see different standards being applied.
Great. And I think the final question for this round is, we have an MCC with a few number of drives. What do you suggest for harmonic filtration, a central AHF or individual low harmonic drives?
That question I would like to answer in a few slides or two.
Yeah, That's a good one. And then, yeah, that's great. Excellent. And we really appreciate, folks, all those questions. Keep them coming in. And if there's anything that wasn't answered or you want more information on, then please reach out to us after the webinar. We'll be sure to clarify anything there. So thanks, Gregor. I'll let you plow on with the presentation and we'll come back to questions in a short while.
Yep, let's take the poll. Maybe you can assist me there. There was one, John.
Sure. So here do you prefer a specific mitigation technique? First answer is I prefer the most efficient technology. Second one is yes, active front end. Third is passive mitigation. Fourth is active mitigation or others. And we'll leave the poll open for another couple of seconds. I see the answers are continuing to flow in. We have over half the attendees have now answered. Let's see if we can get to 3/4. Fantastic, great. So let's post the results. We have, Gregors, you can't see this, but 44% of the audience prefer the most efficient technology. That's fantastic to hear. Then we have 28% have a preference for active front end, 20% have a preference for passive filtration, and 8% on active, and 0 for others. So very interesting feedback. Thank you for that.
Very good. Yeah, that's great. That actually leads me to the next section of this presentation, looking a bit more on mitigation equipment and what you can do to reduce harmonics. As said, in many cases, you don't need to do anything, and you shouldn't do anything if it's not needed, because it's just a waste of money. But you will see situations where you probably would need to add mitigation equipment. So the first two standards that you see up in the right hand or the left hand corner, sorry, you have, for instance, a micro drive without a DC choke. You can see the current distortion here is 105% total distortion. And these are actually the drives talked about earlier, below 7.5 kilowatt, where you have a relatively high distortion level. And you should use them only in situations where you have very little loading on your transformer, simply because you will end up generating a lot of noise when you have hundreds of these in your installation. So be cautious with drives without DC chokes in general. Then you have the standard solutions. That could be Danfoss drives. It could also be ABB, Siemens, Schneider, Rockwell, not just Gamma, they're actually over here, but some of the other drive manufacturers all have built-in DC chokes. That's becoming standard in the market. Danfoss was actually the first manufacturer to build in DC chokes as standard in our drives. And that has now become the market standard, you can say. So when you're buying a premium drive today, they more or less all of them have built-in DC chokes or AC chokes. And this gives you this around 45% current distortion. How much it is specifically depends on your installation, because this value is not a fixed value, it's a value that varies with your system impedance. Then you can add low harmonic drives, which is a combination of a drive and an active filter. It goes as low as 4% current distortion. It brings you almost a sinusoidal current waveform, and that could actually be a quite neat solution when you have a very high demand for mitigation. It has the benefit of being very stable for imbalances on the grids. It has a benefit of actually having the ability to disconnect the filter, so the drive is only running when the mitigation is not needed, which could give you higher energy efficiency, and some other benefit of that solution. Then we have the passive filters down here in the lower left corner, and you can see Danfoss offers two different versions, 5% distortion and 10% distortion, giving you THDI of 5 and 10% respectively. So again, depending on how far you want to reduce the harmonics, that could be a good solution for one or several drives in an installation. 12 pulse is also an offer that we have. we have active filters available, and last but not least, we also offer active front-end drives. So when you look at the Danfoss portfolio, it's very intense. There is a lot of different solutions, and the reason why we are offering so many different technologies is simply that there isn't one solution that fits everything. There isn't just a wonder of the world that has the best performance with the lowest energy efficiency or the highest energy efficiency, that is perfect under all grid conditions, that is perfect under all load conditions. So it's always a trade-off you have to do when you have to select your mitigation equipment. I'll put in an example here for you, and that's why I sometimes are a bit afraid of the standard in the market. And now I also heard 28 of you have a preference of active front-end drives. And active front-end drives is a fairly good technology. We also offer active front-end drives at Danfoss, but it's not always the best solution for harmonic mitigation. There are three main reasons for that. First of all, if you look at the losses for an active front-end drive, you will see that the front-end part adds significant losses to your system. So when you look at a loss ratio of your drive, you can see that 1.6% of the losses is coming from the motor side. You have 0.1% coming from the DC link. And now when you add switching devices on your input side, you have added another 1.6% of losses, plus the losses of the LCL circuitry in front of the drive. And now you end up with losses somewhere around 4-5% of your installation. And when you're running a pump or a fan that runs 24/7, these extra 2-3% of losses that you have added to the system simply means that you will have a very high energy bill each and every month due to the more losses that you have generated. Below the curve here, you can actually see some measurements that we have done in the lab. This is a passive solution compared to an active solution with 100% loading with different speed. And you can see how it changes. So it's not a fixed value. You cannot say that it's always 2% or always 3%. It really depends on where your loading is. If you do the same with a 50% loading, so not running 100 kilowatts, but 50 kilowatts out of your drive, for instance, then depending on your speed, you will see differences between 3 to 8% on your energy efficiency. And if you have a pump where you have a lot of different loading on your installation, these 3 to 8% calculated for every hour that you're running your installation will mean that you will pay double or triple of your energy bill for an active front-end drive solution compared to a standard drive or a passive solution for your installation. So be extremely cautious and make sure you evaluate energy efficiency values when you do an AFE installation. And maybe here you should again be a bit cautious. There have been some standards now applying for drives that you have to publish your losses in a given way for standard drives. Unfortunately, AFE drives has not been considered in this standard, and that means that your AFE supplier will not, as a general term, give you the loss ratio, but you should ask for them so that you can actually do your return on investment calculation for it. The second part is, of course, that it's fairly expensive. AFE drives normally cost around 0.7, 0.8, 9 more than a standard drive. So you're typically paying double the price for an AFE drive compared to a standard drive. So if you're not needing mitigation, don't consider adding an AFE just for safety reason. It doesn't give you anything. It's just a waste of money. And then last but not least, another thing you should be aware of is that the AFE solution is not removing harmonics. They are moving harmonics. So they are maybe cleaning up the lower frequency range, but then they are generating more noise in the higher order harmonic area. And this is something that you can do because there are no regulations in the 2 to 150 kilohertz area. Yet that will come. There are work in progress to improve this situation, but presently there are no standards in this frequency range here, and that means that AFEs are actually allowed to generate a lot of noise on your power network in the higher order harmonics. And if you really look at this, it will introduce a risk of resonances on your supply. It might resonate with EMC filters, other drives where you will see overheating, you will see things simply falling out of synchronism or stopping due to resonance issues if you have a lot of AFEs installed. So AFE can be a very good solution, but it needs to be done with cautious, I would say. And then last but not least, if you are applying AFE drives in general, you should be aware of your grid conditions, because for some AFEs, if you're loading that with standard load profiles from the EN standard, you will see that the current distortion is actually not 5%, it's probably somewhere around 70%. So 5% is, yes, that's correct, or 3% some even claim, and that's perfect for a perfect network. But the more distorted the network is getting, the worse the performance of the AFE is also getting. Then I took an example here just for explaining what you can do in an installation. This is the last slide, I think, or the last two slides. This is an example of a desalination plant, a fairly large plant we did. Here you have a medium voltage coming in to your factory. You actually have two supply lines from 22 kilowatts coming into your factory, and then you have full redundancy so that you can actually disconnect or connect your full supply from either the one FET or the other feed of power. Then you have a lot of drives up here on medium voltage level, 6.6 kilowatts, where you have both direct online motors and motors fed from drives. And you have maybe also some additional drives here fed from medium voltage down to 400 volts, fed and driven by frequency converters or VSDs. The reason why this installation was done was to achieve full redundancy, and that means, for instance, that you can disconnect one of the supply line, so one of the transformer can explode, and then you can supply the full desalination plant from the other. But that is only during emergency operation. So normally you would do two calculations here. You would do one for normal operation mode, and then you would do one for emergency operation mode. And then you will analyze the harmonics for both situations. Before you go there, there are actually some few things you could do to reduce harmonics already in your design phase. So the first thing to do is actually to consider if you can change some of the transformers. In this example here, I chose a different transformer here. The one tapping of the transformer is now with a phase shifting. So you're doing a SCSI 12 pulse, and that means that the fifth order from the one drive is compensating the fifth order from the other drive simply because of this transformer setup. You can do the same for some of the other installations where you simply, because of the angle changes, you can actually phase shift the transformer or the harmonic angles so that they are compensating out each other, and that will improve your situation. And it doesn't cost you anything because the transformer is needed anyway. So it's a cheap way to reduce harmonics if you have the ability to actually consider these moves already upfront. Then, as said, what you need to do as a second step after you have considered this is actually to do investigations under normal operation mode. So what happens if it's running fed from two transformers separated in the middle? And in this specific case, I actually calculated the different PCC levels, so PCC1, PCC2, PCC3, and so forth. And I found out that there were no areas where I had very high voltage distortion. And that means actually that under normal running conditions, I don't need to do mitigation. There is no need for adding harmonic mitigation if I'm running at a normal loading condition. It's only when I have the emergency mode that I need mitigation. So when one of the transformer is shut down or out of service or exploded or for other reasons, and everything is fed from one transformer, then if you do the same analysis, you can see that one of the load points down here actually becomes into the red zone with a very high voltage distortion. And that means that you can actually apply an active filter down here that you only activate when you're running in emergency mode. And that means if you do this, instead of just putting AFE blindly to everything here, the investment that you can save is significant. We're talking about 100,000 euros a year in power consumption if you would just blindly apply AFE to this installation. So it's not small money, it's really significant, and you need to be extremely cautious when you're applying mitigation equipment. You need to do your analysis, you need to do the right thing in the selection. I have another example here from a hospital where we had 25 smaller drives and 4 big drives. And here, again, there were 2 alternatives. Either the supply was fed from a transformer or it was fed from a generator backup. And when we do the calculation, you can see that the mitigation again was only needed when you're running a backup generator, even though the generator was much bigger than the transformer, actually twice the size. You can see that the impedance of the generator simply makes the voltage distortion go up. And again here, instead of adding a lot of mitigation equipment, you could add one single filter that only runs in emergency mode. And in this specific example here, the added costs of the extra filter here, so you pay more for the installation up front, but you will see that the saving here is significant, and you will have a break even after 2.2 years, even though the installation is more expensive with the active filter compared with active front-end drives for only the bigger drives. And the reason for the saving is simply, again, the energy efficiency that you have here. Then I think we're ready for another round of questions. That was the last slide I wanted to show. We're also moving close to the end now.
Very good. Yes, so final poll, or sorry, second to last poll. What would you do if you run into harmonics issues in future? Ask a colleague, friend for advice, contact a third party, always use mitigation equipment to be safe, or can't contact Danfoss experts or others. So we have close to half of the people have voted. We'll just wait another couple of seconds. And I think we can close it there. The audience have been very kind, Gregors, and 55%, so a little bit over half, have said that they would contact Danfoss. So thank you for that. 23% are saying always use mitigation equipment. 9% asking a colleague or friend, and 9% others. And then we have 5% also contacting a third party. So that's good to see. So great. Back to the slides, and I believe we have Q&A now. And I have, again, a lot of questions lined up. So let me move to that screen and find the questions that we haven't answered yet. So to evaluate if our drive complies with the values indicated on the standards in LV and/or MV, we must always use a tool such as the one shown, or is it also necessary to carry out measurements in the field?
Very, very relevant question. It really depends a bit on your distortion level. So I would say that under normal circumstances, I would only do the calculation simply to make sure that you don't have to go out and do analysis on site. Of course, when you have a lot of distortion already, let's say that you have a plant that is already stressed, you have a lot of drives already installed, and then you cannot just automatically say that there is no distortion already there, and there you need to go out and evaluate how much extra you're allowed to put on top of what is already there, and there the analysis on site is needed. But for new installations where you don't have a lot of drives already attached, you can actually do it without. And maybe one thing that I didn't mention here in the tool, you can actually go in here and specify in the tool a pre-distortion level. So if you say that I probably already have 3% voltage distortion on the supply grid before I start installing anything, then you can put in the value here, and then you can recalculate. It's of course difficult to do exact because you don't know the angle of the different harmonics, you don't know how big the individual harmonics are, but this at least gives you an indication of the total distortion. So I think this is useful, but it's not perfect. So it's something to be aware of.
Yep, very good. Then we have a question related to the higher order harmonics with the active front end, so the 2 to 150 kilohertz range. Is this also an issue with active and passive filters?
It's also an issue with active filters. No matter what you have of active in-feed converters, they are having switching frequencies, and when they're switching towards the grid, you will see higher order harmonics being generated. How much they are smoothened out, how low we are going in the distortion level depends on the different technologies. So you need again here to ask your supplier for specific data in that range to make sure that you're not running into issues. Passive solution doesn't generate higher order harmonics, so they are just smoothing out everything. So when you have a passive filter, they have a tendency of removing all distortions, and they are actually removing higher orders better than lower orders. So passive filter actually has an even better benefit in the higher order than any other solution has.
Interesting. There's a question here. Have you accounted for the energy regenerated and supplied back by AFE system in 4-quadrant application when compared to passive filters?
No, and that's also why I say that AFE is sometimes a very good solution, because as soon as I would have regenerative energy into the grid, I would definitely consider AFE solutions.
Yes.
That could be a crane, that could be elevators, that could be other parts where you are actively in-feeding energy all the time. It could be solar-fed converters, it could be many different things. And there I think AFE is a fantastic solution.
Yes, but of course we see a lot where AFE is used in a non-regenerative form.
We've seen quite a substantial amount of AFE simply applied to reduce harmonics, and yep, that's not always a very good solution.
Next question is, what could be the possible reason when we measure even harmonics on the input of the drive?
Yeah, again, very good question. Normally, when you have a three-phase drive, you would see a typical harmonic picture where you have fifth order, you have seventh order, you have 11th, and so forth. You will not see triple order harmonics, so the third, the sixth, the 15th, everything that is multiplied by 3 or divided by 3, you will not see. And then you will normally not see second order either, because that's typically something you see from single loading. If you are seeing even harmonics and third order, that is because you have imbalance on your grid. So your phases are not completely balanced out. And that could, for instance, be that you have a mix between three-phase and single-phase loading, and that would simply pull some of the phases so that you don't have the 120 degrees phase angle, or you have higher loading on one phase compared to the other. That generates some imbalance on your grid, and that again impacts your drive performance and make the drive pull third order, second order, even harmonics.
Sorry, yeah. There was a question, Gregors, that we said we'd handle later, and that was the MCC with a few number of drives. What would you suggest for harmonic filtration, a central AHF or individual low harmonic drives?
Yep, and here I have to come back to this picture here. You simply have to go in and evaluate. There are maybe there's actually a backup slide. Let me see if I managed. Here we go. This slide here. Now I just need to duplicate this screen again. So some of the things that you need to go in and evaluate when you have an installation like that is what is your load profile? Do you have a lot of light loading? Do I have a lot of peaks? Simply, as you saw before, maybe you can actually leave mitigation out for a given period of time, which gives you energy savings. You have to look at your physical space constraints. Are there room enough for adding passive filters to everything, or is a central solution better because there is less room? You need to go in and evaluate which standards you need to comply with. You need to evaluate power factors and efficiency of your installation. Passive filters are not necessarily always good either, because if you have a lot of light loading on your trend or on your passive filter, then there is a tendency that the passive filter is giving leading power factors, which could also be a problem. So there is a lot of evaluation you need to do for specific installations. We have done a lot of installations with active central mitigation active filters with success. We have achieved installations with very, very high energy efficiency with active filters centrally compensating. So it could be a good solution, but it's not always the right solution either.
Great. A follow-on question, I believe, to a previous one. We have even order harmonics. Can they be mitigated with AHF?
Yes, that will have a positive effect, definitely. You will probably see it in front of the AHF filter still, but you will not see it inside the drive. So the imbalance that you're generating will still be there, and that means that the drive will react to it, so you'll still see even harmonics. What you should be doing is actually look at the source of the second order. So can you change the loading? So can you move some of the single phase loading from one phase to another phase so that you have distributed your single phase loading more evenly. That would be my advice. Or you could consider adding filtration in front of the single phase loading, simply to get a better balance on your power supply.
Great, thanks very much, Gregors. That's all the questions we have. We have one more poll, guys. Actually, sorry, we have one last question coming in. Can you please explain the resonance effect?
Yes, it's let me see how I do this. It's just like hitting with a hammer on a bell. So if I take the picture here again, if you look at this picture down here, everywhere where you have a peak, you have a resonance, but it's not necessarily generating issues unless there is something in your installation that has the same kind of performance. If you look at your power supply, there might be a drive that has a resonance point, let's say at 8 kilohertz. And now you have something that is injecting current at 8 kilohertz. And that means that you have a hammer that hits on this 8 kilohertz. And the noise of the bell depends on how hard you hit. So the bigger the peak becomes, so you might not have a problem with 8, but you will definitely have a problem if you're hitting very hard with a hammer. So the peak here depends on, you can say that's the strength of how hard you hit with your hammer. So here you might hit a little here, but it's actually so little that you will not see any noise from the bell. As soon as you start having these peaks, that's actually where you start hitting so hard that you will see the noise coming out of the bell. Or said in other terms, this is where you start erecting harmonics on your power supply. And that is erecting with other equipment. That could be a power bank, it could be a drive, it could be other equipment that is vulnerable towards frequencies that is injected here. And that means that the energy will now go from the filter that is injecting into the vulnerable part, and the vulnerable part will react by sucking up the energy and requesting more, and the filter will just start erecting the harmonics. And at the end of the day, if it's an EMC filter in the drive, the EMC filter will explode.
Very good, excellent. Gregors, as always, very informative session. I've also learned something new today. Thank you very much for joining us. We have one final poll for the audience, if we can launch that one. And this is, guys, to ask you, what would you like to hear about next? So, Gregors has talked about harmonics today. We know that's a hot topic. What would you like to hear from us next in our next Drives Club webinar? Would you like to know more about common mode voltages or correct installation practices for variable frequency drives, condition-based monitoring and preventive maintenance, or then connectivity in drives to support digitalization trends? So what would you like to know more about next time around? And I can see people are voting. We already have over half the people have voted. If we can just leave it a few more seconds, we can then already today announce our next topic. Although there's two very close, they're neck and neck. They're actually more or less the same. We can close the poll there. And by a very, very small margin, common mode voltages wins by getting 32% of the vote. So rest assured, guys, we will have that as our next topic. And then for sure that directly after that, the next topic will be connectivity and drives at 28% of the vote. And then we had the other two at 20% each, correct installation practices and condition-based monitoring. So that's it for today, folks. We thank you once again for joining. We're bang on time, and we will send all of the information after the webinar. And we thank you very much for your kind attendance, and we look forward to seeing you again soon.
Yeah, and also a warm thank you from my side. Very good questions. You are extremely talented. I can hear from the questions that came in. Very good, and thanks a lot for the cooperation here.
Yeah, they kept you on your toes, Gregors, right?
Yes, exactly. That's nice.
Very good. Thanks again, Gregors. Thank you to everybody that joined. Bye-bye.
Bye for now.